Okay, so this is lecture number 2. And in the last class we just talked about where all we need phase lock loops, and the conclusion was that we need some kind of clock source ranging from maybe a few megabit, few megahertz to gigahertz clock depending on the application. Okay, so in order to generate such clocks we need that. Then we looked at crystal oscillator, and we told that this crystal oscillator can be modeled like an RLC circuit, but the frequency of the crystal oscillator is limited, so we cannot get whatever frequency we want. We need to have much higher frequency. Okay, and in order to have much higher frequency, we can have different inductors and capacitor. And then we figured out that if we have a simple inductor and capacitor, then in that particular case you are going to have an issue, because you cannot have sustained oscillations. There is a resistor associated with the inductor which will make the oscillations to die down. So we have to come up with something which can keep this frequency of oscillation sustained, right? Which can be tuned and so on, and that is where I told that this is the place where the PLL comes in. Okay, so let me just go back to this our oscillator case and tell you what kind of signals we are looking at the output of such a block which produces sustained oscillations. So I will start with LC, and just because this is quite common and you have seen this circuit before. So let us say we have this RLC circuit. There is surely going to be a resistor in parallel with the LNC, right? And we are looking at this V out as a function of time. What we want if we want to have whatever frequency of oscillation we need, we can change that frequency by changing actually changing these values. Okay, so let us say I am just plotting this with respect to time. We have this V out by T, right? So what we want is an ideal sine wave. Just assume that this is an ideal sine wave, and I am going to repeat this sine wave. Okay, that is what we should have, right? The exactly same waveform and so on. So this particular signal, if you look at it, the signal V out of T is nothing but if I say that this amplitude is +1, so I can have this as sine of omega naught t, where your omega naught is equal to 1 by under root LC for a given LC circuit. Okay, is this part clear? So this is, if I have this particular whatever this LC circuit is, if it produces sine wave which has such kind of output waveform, then it can serve as a clock to my system. Okay, and how multiple things here are related, frequency and other things. So this is the time period of the sine wave, everyone knows it. So I have my omega naught, which is normally called as frequency of the clock in radians. Okay, these radians is the unit, and omega naught is equal to 2 pi of f naught, where f naught is frequency of the clock in hertz. Okay, in hertz, and f naught is equal to, or you can say the time period of the clock is t is equal to 1 over f naught, which is time period of the clock. Okay, so these are just the parameters which are used in reference to a clock. Okay, now what happens is that in a real system you are not going to get such kind of ideal clock. Okay, so what is going to happen in reality? In reality, you may have, maybe you start with the 0 point here. Okay, just a minute. Yes, you may start with the 0 point here, and then you may have some wiggle along this axis, and then your zero crossing may change, and you may have some kind of you may have another change in the zero crossing, and this is the kind of this is exaggerated, but this is the waveform you may receive. Okay, so what happens is, and why do you get this waveform? Because there are noisy elements in the circuit. Okay, so it's like, see, if you have this resistor, then you cannot get fixed sine wave output, so you are going to add some other kind of circuit in parallel or somehow, such that you get always sustained sine wave, maybe of roughly the same amplitude. But when you are going to do that, you will have variation in the output clock waveform, and that variation in the output clock waveform is going to change not only the amplitude maybe, but also it will change the zero crossing of the clock. And if you remember, we were looking at zero crossings of the clock when we were trying to fix the when we were trying to send data rate at a fixed like fixed megabits or gigabits per second. Okay, so in case of clock, what is more important for us is not this amplitude is not that much of importance. The important part is when my clock crosses the zero. If we are looking at rising edge, then it's rising like going from minus to plus or plus to minus. You can look at both. Okay, or both can be used, because these zero crossings mark an event in the system. Event is going from low to high, or effectively to say it's a rising edge. Okay, so this particular thing is you can say it's characterized by either looking at phase or frequency of the signal. So let me just plot the phase and frequency of the signal. So for the first case, where we have that blue curve, which is an ideal sine wave, that particular blue curve has fixed frequency, and that fixed frequency it remains same all throughout. This is an ideal case. So if I plot f, this frequency value remains f naught, which is 1 by 2 pi under root of LC. Okay, but for the magenta one, where you are seeing the variation in the timings, you may see the frequency may drop, right? If you just want to look at it, you can say that, okay, my time period has increased, so maybe my frequency has increased, frequency has reduced actually, right? And so you may have some kind of different frequency in the system because of the variation. Okay, for this particular sine. Similarly, if you look at the phase of this signal, what is the phase of the signal? Phase of the signal is the argument of your sine wave. Okay, if omega naught is varying, then your phase will also vary. So you can say phase of the signal is nothing but frequency integral of time. If omega is fixed, then it will be omega naught t. If omega is not fixed, then the phase will keep on varying. Okay, so if I plot the phase of the signal, it may, so let us say it starts from 0, right? For an ideal sine wave, it will cover a phase of 2 pi in one time period. So I will tell you how it does that, right? For an ideal sine wave, it will cover phase of 2 pi in one time period, and then it will go to 4 pi in another time period. So this is 0, this is 2 pi, and this is going to be 4 pi. This is what is going to happen for an ideal signal. I am plotting phase with respect to time. How this phase becomes 2 pi? So if I look at a phase from 0 to time t, which is the time period of the signal, omega, if omega is fixed, omega is nothing but 2 pi by t, or 2 pi f naught times dt. You integrate it, you get 2 pi. So the phase is accumulating like this. Now what is going to happen for the other sine wave which has actually this variation? For that particular signal, you will again accumulate a phase of 2 pi, but slowly, and that phase accumulation 2 pi may happen at the different rate, right? And so you may have this plot is not as per scale, but this only marks the variation. Okay, so this may have it, sorry, this is like it gets a phase of 2 pi slightly away, it doesn't get at the exact point, so maybe I can just say here, right, and then the phase is different. Okay, so if you look at the sine wave signal, you see in the two cases, one is an ideal, the blue one is an ideal clock, okay, the magenta one is a clock signal with some kind of perturbation. So for both the signals, amplitude variation you can very well see here, or the voltage you can very well see here, but what is more important is the variation in frequency and the variation in phase. Okay, and why is this variation in phase and frequency important for us? Because when we are using clock, okay, to synchronize our system, or to to have a fixed data rate or something, we are making all the decisions based on some event. Okay, by the way, that event can even be the peak value. Even the peak value can be treated as an event, right? But treating a zero crossing as an event is much easier in our system, right? So the zero crossing is quite important, and that is why we look at this particular pulse as a so we look at this particular pulse as our clock waveform, and ideally this should repeat, okay, without any changes. Right? Now I can come up with another thing and say, let us say I am doing all kind, this is, just a minute, yeah, so I am doing all kind of zigzag, I start from this point, I do all kind of zigzags here and there, maybe much more, but when I cross 0, I cross at the right point, and then I again do a lot of zigzag, and then I cross another 0, that is also at the ideal zero crossing location. If I do that, okay, and if I am only interested, it depends on application, if I am only interested in zero crossing, right, it's fine with me, because my events, my rising zero crossing going from negative to positive is fixed, and which marks an event in the system, and I am going to synchronize my data rate or other things, or even the sequential logic with the rising edge. okay, or zero crossing. So it may have more zigzag, which is like you are having a lot of voltage variation, but till the time you keep this fixed, it's fine, okay, because your event remains fixed. Okay, do you have any question with this? Yes, guys, if you are listening, you may have one or two questions at least, or no? If someone told my voice is not clear, is it clear now? Okay, so do you guys have any question? Okay, so let me continue. So what we need here is, yes, someone is speaking? No. Okay, so what you see here is that in an ideal clock case, you have a fixed sine wave or a fixed clock period. In a real, these things are going to vary, and so the frequency and the phase of the clock will also vary. Okay, now these things have been characterized in the form of some metrics, which let me tell you. So if I have, let me see if the paste option is there. Yeah, this is good. So if I have an idea, this is my ideal sine wave, for example. I'll show you here. Yes. Okay, so let us just look for two sine waves. So this is my ideal clock. Right, and there is a certain zero crossing. This is my ideal clock. Now let me just say there is some real clock, and real clock is like it may start like this. Yeah, tell me. What do you mean? What do you mean by inverted? How can it have that if it's if it is something kind of a resonator? So what you are the question which you are asking is this. Let me just come back to your question. So the question which you are asking is that if I have first cycle is like this, okay, and the second cycle is like this. Is it what you are saying? Okay. So where can you have this? Tell me. No, here what do you treat as a clock? Question is that. So a clock is some system which is periodic in nature. Okay, some system which produces signals which are periodic in nature. Now what periodicity are you looking at here? So where does it, so the zero crossing which it has, this is one zero crossing, this is another zero crossing, this is another zero crossing, this is, and this may be the another one. So do you have a zero crossing here? So what do you miss? Okay, so this cannot be treated as a clock unless you are defining your own system that okay, I will get rising edge here, I will have this zero crossing, then there is no zero crossing, then another zero crossing. If you want to treat it, treat that way as a clock. So there is a periodicity in if let us say whatever we have drawn here, this thing repeats, okay, then surely it is periodic, but the periodic events are not like a simple sine wave. They have some other periodicity. Do you understand that? Yeah, so by the way, you have introduced this thing here, but this is one part of, you can say, some modulation scheme where you just flip the signal. So the information, this is used in RF, the information lies if you are having a positive, you can treat this as a positive bit and this as a negative bit. Okay, so you can treat that. It's like this, I can have a sine wave and I multiply my sine wave. Okay, I think it originates from there. Maybe your question was not at that point. So if I multiply my ideal sine wave with such kind of signal, okay, a sine wave which is shown here in blue, if I multiply with this such kind of signal, then whatever you are seeing in the output you will get that. Okay, and this is like modulation of the clock signal using some kind of information. Okay, so coming back to our clock signal, so we, yes, due to what? Okay, if you are having multiple zero crossing, this is like a really bad clock. Okay, surely you can have it, right? Depending on how you design the clock, you can have it, but that is going to be a really bad clock, and you would not like to design such a clock source. Normally in the presence of noise, okay, it will have only one zero crossing. It will not have multiple zero crossing. A good clock. Oh. Yes, tell me. Okay, so now if we look at this ideal sine wave, okay, and you look at the magenta one, which is, let us say, a real sine wave. Let's say it's a clock, right? And what you see here is that there is a difference in the zero crossing of the two signals. One is here, so let's say I am only looking at the positive edge for now. I am not looking at the negative edge. So we can look at both the edges, but just I want to reduce my workload, so I will look only at the positive edge. Okay, so the quality of the clock which you are going to see, that depends on how much error you are going to have at the zero crossing with respect to the ideal clock. Okay, so if I see here in the first case, if you look, the first zero crossing of the real clock is happening delta t time after some the real clock. So if I mark my real clock edges, they are all having transitions are happening at 0, then at, if t is the time period t, and then this is the time period 2t, and so on. This is like ideal case. Okay, the error which you are going to see, if I just write t of 0, t of 1, t of 2, and so on as the timing instant at which my real sine wave crosses 0, right? Then t of I minus k, or t of I times I plus 1, not I plus 1, I times t. This is going to be the timing error between the ideal rising edge and the real rising edge. Okay, so it's like here I see t of I, this is happening at some t naught instant, so delta t of I is t of 0 minus 0, which is t0, delta t of this is 0, delta t of 1 is equal to t of 1 minus t, delta t of 2 is equal to t of 2 minus 2 times t. So this is the error in the rising edge, or my negative to positive clock edge of the real sine wave with an ideal sine wave. Okay, so what we can say about any system is that in the presence of noise, okay, noise is random. In the presence of noise, this delta T0, delta T1, delta T2 and so on, these are nothing but just random variables. Okay, they are nothing but random variables. And if they are random variables, right, then they are going to have some mean, some some standard deviation, some maximum and some minimum value. Okay, so what we can say here is that these random variables, right, if you want to write this delta T1, you can also say this is so let's not write anything here. Let's this be T on. So these are random variables. They will have some mean and some standard deviation and so on. Now my question to you will be, if I want an ideal clock, what kind of mean and standard deviation would I like to have with the real clock, with respect to the real clock? Okay, so can you, if I tell you that there is an ideal clock and there is a real clock, okay, and let me just tell you, let us say there are two real clocks. One may be like this, okay, this is another real clock. So surely you see that the green clock is having a lot of variation in the timing by now. So if I just ask you, so I will just name this also. Let us say the magenta real one is number 1 and the green one is number 2 real clock. Okay, so just if you look at and let us say the average time period of both real clocks, magenta 1 and that green 2, the average time period is same. Let's keep that way. Okay, so what can you comment on standard deviation of the clock number 1 and number 2? What do you have? Greater, lesser, equal to? If you just look at these two clocks, for example. So can anyone tell me? So what you see is for the green one it is greater than your magenta one, right, number 2, and because you see that there is a lot of variation. Okay, this is just pictorially, but in reality if you have this, then you will say that the green one is having a lot of deviation. So which one will you prefer, magenta one or green one? Magenta one. So whichever has a lesser deviation, that is something which you are going to prefer. Why? Because the variation of that clock with respect to an ideal clock is actually lesser. Okay. So now if you think about it, we can measure how good the clock, real clock is by measuring the mean and standard deviation and max and min, because once it is a random variable you will also have some maximum and minimum value depending on how many samples you are going to choose. You will find how much variation you are going to have in terms of zero crossing or in terms of events which you are going to have. Okay, so ideally speaking, for an ideal clock you are going to have a standard deviation which is signified by sigma. This should be 0, ideal clock. This is 0. The max value, max and min, both deviation on this delta t should be equal to 0. This is an ideal case, right? But we know we will never achieve an ideal system, so they will have some value. Whichever is going to have a lesser value, right, that will be a better clock. Okay, so this is the kind of metric which we are going to use. Now, if I ask you, in order to judge how good my clock is, what did I use? Did I use voltage values like any peak values as shown here, right? Or actual amplitude? Oh, it's not encircling with the correct one. Yeah. Any of these values, or we looked only at the zero crossing? Right, the answer is that we looked only at the zero crossings of the clock. Okay, so the information is information which we would like to have is a perfect zero crossing without any deviation. Amplitude, it can vary, it may be fine. Okay, so far in all your other courses which you have done, you were more worried about the voltage, but here you are not worried about the voltage as such, the whole voltage, amplitude and other things. You are more worried about zero crossing because that marks an event. Okay, now this particular zero crossing, see this delta t and so on, whatever you are having, it's like delta ti. If you have delta ti is not equal to 0, then you can say the time period of the clock is different, or the frequency of the clock is different, right? In the same way, you can also say, as I have shown you here, right? The phase which you are going to accumulate by phase is an integral of frequency. The phase which you are going to accumulate by a real clock is going to be different from the phase which you are going to accumulate with respect to an ideal clock. Okay, and this delta t error which you are seeing here, which I have noted in terms of delta t, this is directly related to the phase error. Okay, they are just like other way of looking at it. Okay, if I am having any if I am having any timing error here, the same timing error is reflected in the phase error. Okay, and how can we find that timing error, the phase error between the two? We can find the phase error. There are two ways to find the phase error. One way is, what is the phase accumulated by an ideal clock, which is going to be omega naught, which is fixed, times dt. Okay, let us say this is 0 to t. And the phase which is going to be accumulated by a real clock, phi real of t, this is whatever frequency it has, this will be 0 to t. This is the real clock. So the phase error between the two, I can write delta phi, or let me just say phi error of t is nothing but phi ideal of t minus phi real of t. This is my phase error. Okay, and if you look at this waveform which I have shown you here, there is, see, if there is a separation between the zero crossing of the two clocks, let me just remove this part, right? If there is any separation between the zero crossing of the two clocks, and if they start with the same point, the same separation you are going to see here, because whenever a clock completes one time period, it will accumulate 2 pi. So this is going to be the phase error here. Okay, both of them are actually having 2 pi values at this edge point, at this line, right? But the separation between the two is proportional to the timing error between the zero crossing. Okay, so this particular value is going to be 2 pi times delta t, whatever is the timing error by reference time period which we used for the phase. Let me just elaborate on this because this will be a critical part. So let us say I have this as an ideal sine wave. Okay, let me place it. Yeah, this is an ideal sine wave, and then I have another sine wave which I am just stretching it. Okay, so let us say this is what I have as another sine wave, right? So only look at right now the first zero crossing. Okay, and okay, oops, paste, and let me just squeeze this. Okay, so let us say these are the two sine waves which you are seeing. Blue one is the real ideal one, and the magenta one is the green one. Magenta one is the real one. Okay, so if I have this particular clock, right, they both start with 0, but they both cross the next 0 at a different time. Okay, so if you look at it, this is my ideal time period t, and then I have a real clock. The first real clock time period t1 is different from the ideal clock, right? If you look at the phase of phase, so if you, let me just write it, phi of ideal, right, in time period t, how much phase it will accumulate? Phi ideal of t is nothing but 2 pi by time period t times dt. We are integrating till 0 to t, so this is 2 pi. And phi real of, I am calculating within the same period. Okay, so this is same for my calculation. Okay, but the actual frequency of the real clock is t1 times dt. So what you are having here is 2 pi t1 times t here. Is it correct? So you are going to have a difference between phi ideal and phi real. Okay, and this particular difference is it can be related as phase, can be evaluated as phase error, which is phi ideal of t minus phi real of t. Okay, so if you look at phase error, or you look at the timing error which I have shown you here, this timing error delta t, I can have the same thing, right? I can say that the second rising edge, here I write t of 1 minus k, or delta t timing error is t of 1 minus t. And what is t of 1? The first rising edge comes here at t1 minus t. This is the timing error. Okay, so you see that we are having the metric which we are, if you look at a timing error, right, this is telling me the difference between the two rising edges. If you look at the phase error, by the way, this is nothing but 2 pi into 1 minus t by t1, which is, I can say, 2 pi into t1 minus t by t here. Sorry, this is t1, right? So now what we can say here is that if you look at it, this timing error and this phase error, they both are related. Okay, and in a given any real system, this t1 right? The average value of the T1 will be same as T, but instantaneous value will keep on varying. Okay? Do you guys get that? Is there any question with this? Okay, if there is no question, so now the thing which I want to tell you is that the phase error or the phase and frequency of the clock, right? Here the frequency varies, here the frequency remains fixed. The phase and frequency of the real clock tells us phase and frequency of the real clock tells us how good or bad the clock is, because they are going to directly affect the zero crossing of the clock signal. And this clock signal marks this, this has a significance because it is an event, and if we because we are synchronizing our system, just think about it. Your processor has a 3.6 gigahertz or 3.4 gigahertz clock, and that keeps on changing all the time, right? If that 3.6 becomes 2.4, right, it will be your system will slow down, isn't it? And how that variation in time period and phase and frequency are related, this is something which we have talked about. Do you have any question? Please ask. Yes, Bhanu Prakash, do you hear me? Yes, Bhanu, do you have any question or anything which you would like to ask? No. Okay. So, okay, someone has, by the way, see, when I am writing on this Windows thing, right, I normally do not see the chat window, so please interrupt and ask a question. I see a couple of questions here. So one person is asking, so shape does not matter as long as event occurs at a specified time. Yes, that is true in many applications, but it may not be true in other application where voltage of the signal is doing something back to the system. Okay, so Shubham, is it clear? See, if only the rising edge or only the time is like, okay, whenever I cross 0, I have an event, and I do, and I actually just use that event to synchronize or to do something, it's not a problem. But if the actual voltage waveform of the clock matters, in some cases, mainly in RF, because it leads to some other problems, then the shape matters. Okay. Yeah, the other question is by Neil. He says that due to noise in clock, can we have multiple zero crossing? I think we have already taken up. Okay, why are we not considering falling edges? It's nothing that we do not consider falling edges. We surely consider falling edges also in multiple applications. But just the thing is, let me just tell you. So, in some cases, it is still shared, right? Yeah. So what happens is that in some kind of clock signals, you may have. So let me just draw a square wave. Whether it's a sine wave or a square wave, I can just draw this clock period, right? I may have this. Another, maybe I have this. When you are generating high frequency clock, right, you can have all such kind of options. So here, if you look at it, all the rising edges are aligned, right, but falling edges are not aligned. Okay, and this is normally called as duty cycle error. Okay, so let me tell you, this is T on, T high and T low, right? Duty cycle of a clock is defined as T of high divided by time period, which is T high plus T low. The first one appears to have a 50% duty cycle, So if you are using at this particular clock at both the edges to synchronize your system, right, it is perfectly fine because it has a 50% duty cycle. Other appears to have some 45% and the next one appears to have some 60% duty cycle. Now if you use this particular clock in your system, then you will see that all the events are not synchronized at the same rate. Few events are coming at a faster rate as compared to the other events. Similarly, it will be slower for the other cases. So yes, it is true for synchronization. We may generate a low frequency clock and use both the edges for to synchronize our events, but in that case we have to make sure that we have this 50% duty cycle. If we don't have that, if we have like 45 or 60, we may have some trouble unnecessarily. Okay, most of the time in clock generation it is very easy to make sure that okay, my period is fixed with a less deviation, but making this duty cycle 50% all the time may not be easy in all cases. Okay, it may take some extra effort or something. Okay, so both the things are used. It is not like only one thing is used, that you use only a full rate, that you use only the rising edges. You use both, but duty cycle creates issues. Okay, any other question? Okay, so I have another question. As frequency is not constant for a noisy signal, how do we find frequency with respect to time? Oh, good. So let me ask you, I have a certain, okay, yeah. So I have a signal V, okay, this signal is having some A times sine of omega t, okay, and I tell you that this omega is not fixed. Okay, so now how are you going to find the frequency? Well, we see if this is a sine wave of such kind of system, right, the phase of the signal, because the frequency is not fixed, so what you are going to have, if frequency is not fixed, you cannot write this omega t, you have to write omega dt, because omega is a function of time. It's not about writing, by the way, it is like the actual the correct representation for the signal is this itself. Okay, this is the correct representation if frequency if frequency varies, right? If this is the correct representation, then you will have instantaneous frequency and you are going to have average frequency. You define instantaneous frequency as instantaneous frequency omega will be defined as d phi by dt, right, and whichever time you want, you calculate that d phi by dt at that point, that will be instantaneous frequency. Okay, and once you have instantaneous frequency, you can define average frequency, the variation in the frequency, and so on. Like just an example I will show you here, that this magenta one which I have drawn is an instantaneous frequency which I drew in this manner by taking the derivative of the argument for sine wave. Okay, and the average frequency, if I need to find, well, average is always taken over a certain time, so I am going to say, okay, what is my average? My average is maybe, my average turns out to be, I take the average and that value is somewhat in between the instantaneous frequencies. Okay, so that is how we define the frequency. Okay, if delta Ti is same for every I, then is it considered a good clock? Yes. See, if delta T of I is same for each clock, so the question which you are asking is that in let us say if delta Ti, if all these delta Ti are same, that is not a bad clock. That only means that your clock is shifted. Okay, but you have an error with respect to the ideal clock, that is a separate thing. Okay, so if it is fixed, there is no frequency error in the clock. The clock behaves as good as ideal, and what you have is your delta t is fixed. Okay, so that is as good as an ideal clock itself. Any other question? Okay, so now if you look at it, let me just come back. If you look at it, what we can summarize from today's lecture is that when we are looking for a clock, the things which are important are phase and frequency of the signal, because they are more important than the actual amplitude, because they are the thing which are fixing how good a clock is, or how good we can synchronize our system in real time. Okay, is that part clear? See, we have this LC oscillator. If you look at it, we have this LC oscillator at the top. There is an inductor current, right? There is a voltage across the capacitor, but we are not talking about voltage or inductor voltage across capacitor, inductor current. What we are talking about, the timing, the phase and frequency of the system. Okay, so in PLL, what is going to be important is the phase and frequency variables rather than your voltage and current variables for the clock itself. Okay, so from the next in the next class we will start how to deal with phase and frequency variables. Right? If we want an ideal clock, we want its frequency to be fixed, not voltage. Okay, and we do not want this particular error to change with respect to time. If this error keeps on changing, that means our clock is not good. Okay, so our focus is going to shift from your regular voltage, current, charge variables to phase and frequency variables. Okay, okay, there is another question. Okay, if del t is variable, then the clock have an average fixed time period. It depends. Okay, how it depends? Because if del t is variable, right? But it always keeps on increasing. So your question is only it's a variable. Variable is like a bigger set. It can be variable, but it can be limited. If del t is variable but limited within certain bounds, right, then you can define an average fixed time period. But if del t is keep on changing and it can go anywhere between minus infinity and infinity in real time, you cannot define a fixed clock period. Okay. In the calculation of phase of a real signal, you integrate it from 0 to t. Why not 0 to t1? Also, the term inside should have other harmonics, as it is not an exact sine wave. Well, in the calculation of, you can define with respect to t1, but let me ask you, with ideal and real clock, which you can treat as a reference? I do not know when t1 will come, right? T1 is a variable value. Yeah, so if you treat the reference as the ideal one as a reference, then I will find the phase error with respect to that. Okay. Now, also the term inside should have other harmonics. Now, which is the other harmonic? It's not an exact sine wave. We are looking, so let me tell you, this particular sine wave which I am having, right? Surely this does not have a fixed period. So if you look at the frequency content of this, it will have multiple frequencies, right? But we are not looking of this as a voltage waveform. What we are looking here for this particular signal is the phase of this waveform. So I can very well, just let me tell you, if I write the magenta sine wave, this may be the last question because we are running out of time. If I write this magenta sine wave, sine of omega dt, right? And this is my signal, let us say 0 to t, whichever you want. I can keep my omega as fixed as 2 pi by t1 for t1 period, I can keep my omega another value, maybe 2 pi by t2 for another clock period, right? So I am looking at this variable, I am not looking at the voltage waveform where you are finding multiple harmonics. Do you get that? I think Lanjan, you asked that question. Okay. If noise is the only cause of delta t, then we have the mean of delta t equal to 0 because noise is a random process. Well, in case of PLL, it is not correct. Okay, a free running oscillator or a free running system which is not, this is Bhanu, to answer your question, noise is surely a random process. The noise has a mean 0, right? But in case of PLL and oscillator, the noise accumulate. Okay, and if you do not put in a feedback loop, then the noise can accumulate and you can have a really like an infinite deviation from your ideal clock at infinity. It's not limited. Okay, oscillators are different blocks, there you accumulate noise. Okay, we can have delta t due to mismatch in noise. You can have delta t for any reason. You can have delta t because of mismatch, because of offset, because of noise, because of some injection, because of many things. Okay, so we will see all these things once we start doing the PLL proper. Okay, so let me stop here because we are running short of time. You can post your questions over Moodle if you would like to ask. Okay.